Hey everybody, tonight we're going to try to prove an integer divisibility test by 13. And this if and only if is the old fogey's way of using the double arrows. If and only if is, it's logically equivalent. So an integer n, we want to prove this, is divisible by 13 if and only if the result from removing the last digit, multiplying by 4, and then adding it to what remains is divisible by 13. Now that's a mouthful, but we're going to make some sense of it with a special case right here. Let's look at 2028 and see if we can show that it's divisible by 13 by this mouthful of words up here. So what this would imply, 2028, that would be 202 after you remove the 8, right? So 202 is what left after we remove the last digit, 202. Now to that, we're supposed to add 4 times the last digit. Okay, so that's plus 4 times 8. Okay. So what is that? That's equal to 234. 4 times 8 is 32 plus 2, so you get 234. Now you might be able to tell right immediately whether or not this is divisible by 13, but let's just go ahead and try out the algorithm on this number as well, even though you could probably do that quickly in your head. So let's see, 4 times 4 is 16, and 16 plus 23, so this implies 23 plus 4 times 4, right? Sorry, that's plus 4 times 4, which is 39, okay, which is manifestly divisible by 13. Okay, so that's equal to 3 times 13, right? So 2028 is divisible by 13 if you trust this test right here. And also I believe this is equal to 156 times 13. And a lot of you might say, well, this number is small enough you could have just done the long division if you were that curious. Okay, so either way, but you can see how this test might be more useful for like multi-digit numbers, like in the 10-digit range, something like that. This test might be a little bit nicer. Who knows, you know? But in any event, let's go ahead and try to prove it for the more general case. And it's going to be a modular arithmetic proof. So we're going to just write it in, and I guess it's the standard canonical Hindu-Arabic representation, okay, where all the a sub i's are numbers between 0 and 9 inclusive. Okay, so here's our n. Now let's talk about the remaining piece. And y'all, when I say remain, this r that you see right here, I named that r after this r for remains, not remainder, but r remains, right? This is what remains if you chop off that last digit. Notice since it's a place value system, you have to decrement the exponents here. In other words, a sub n is now the coefficient of 10 to the n minus 1 and so on, okay? Notice that a sub 1 lost a power of 10 because, again, this is a positional system, so that's why you have to write down the remaining number in this fashion, okay? So this part is slightly challenging, at least it was for me, okay? Now, what's the next part? We have to multiply the last digit by 4 and add to what remains, okay? Well, that would be this very next line, okay, folks? Okay, I tried to color code this for you folks. This is 4. There's color-coded green, 4. So this is what remains plus 4 times the last digit, so I just write that down, okay? Now we get a little bit stuck here, but you'll notice that if you multiply through by 10, something favorable happens. You get n right here. This is mainly n except for the 40 a sub 0, right? This a sub n, 10 to the n, is exactly our original number, except we have a 40 a sub 0 right here. Now our saving grace right here is that in modulo 13, 40 is congruent. And this really is the whole thing, really, right here. This is it. 40 is congruent to 1 mod 13. Right, folks? Because 40 minus 1 is 39, which is divisible by 13. It's 3 times 13, right? So you see on the very next line, see how the 40 gets replaced with just a sub 0, and you can put a 1 there for emphasis just to make sure you see this one here is the same as that one there. Okay? But notice this is just equal to n. Okay, and this is our original construction, a representation of n. And so what we've shown right here is that n is indeed congruent to r plus 4 times the first digit. Okay. Okay, and this is mod 13, but if it's congruent to this, it's also going to be congruent to, well, we've just proved, I mean, there's nothing else to write down. Let me erase that. Okay, what we've written down right here proves that n is congruent to this object right here, okay? Because n is equal to this, okay, but it's congruent to this, right? And so this much is true. So that would say that if r, excuse me, let me get that working again. If r plus 4a sub 0 is congruent to 0, and again we're talking mod 13. That's if and only if it's everything's reversible here, so that's if and only if n is congruent to 0. Again, mod 13, right? So that proves it. In other words, if n, that would say that n is divisible by 13, and then r plus 4a sub 0 is divisible by 13. So that proves what we set out to establish, folks, that in either direction, both of these objects are going to be divisible by 13. If one is divisible by 13, so is the other. Okay? So we've proved what we set out to prove. And again, the key step was right here, just this 40 congruent to 1. That's the magic trick. Everything else is just symbol manipulation, laws of exponents, etc. But so anyway, QED, and I guess I should, just to be consistent here, I should put mod 13 here. Okay. All right, folks, and again, I guess that completes the proof. Again, a mouthful of words gets converted to congruence, and we showed that if one is congruent to 0, the other has to be congruent to 0, but that's tantamount to saying that both of them have to be divisible by 13. If one is divisible by 13, the other has to be divisible by 13. Okay, that's all. Thank you.